So hi, I'm Ashwit.
And I'm Pratik.
And in this video, we're going to talk about some basic signals that we will see very frequently in the course. And first, we look at the sinusoid. You can see in the plot that we have a sinusoidal signal, and symbolically, it's written as sine of omega t plus phi. And in these, we see various quantities. So the first quantity we look at is omega, and omega is called the angular frequency. It's measured in radians per second. And in this particular case, the angular frequency is 125.66 radians per second. So you're probably not familiar with this, some of you. The quantity you're probably familiar with is the frequency, which you studied in high school physics. The frequency is measured in hertz or cycles per second, and it talks about how many cycles of the periodic waveform we have in 1 second. So this plot has a frequency of 20 hertz. Of course, it's also important to talk about the fact that the sinusoid is periodic, so it repeats with time, and at every time period, which in this case is 0.05 seconds, we know that the cycle repeats, the waveform keeps repeating and it gets back to where it was. So this is the sinusoid, alright. Of course, the time period is distance between peaks, and I'm sure you know this from earlier classes. So the next signal we look at is the growing exponential. The growing exponential is written as exponential of e raised to the power of alpha times t, where alpha is a constant which tells you how much the exponential grows or decays. In this case, we have taken alpha as 0.9, and when alpha is positive, as you can see over here, the exponential keeps rising and grows over time. Very simple signal, and of course, if alpha is made negative, we get the decaying exponential, and in this case, we take alpha as negative 0.4. Both signals are actually quite simple, but we will see it several times during the course. Alright, so we've studied two types of signals. We've studied an exponential signal, we've studied a sinusoidal signal. We can also combine signals, so we can take the exponential, we can take the sinusoid, multiply the two, and we can get what is called as the exponentially growing sinusoid. And you can see it is represented as e raised to alpha times t into sine of omega t plus phi. And you can see that we have the envelope of the function, which actually is e raised to the power of alpha t, and of course on the negative side it is negative e raised to the power of alpha t. And between that envelope you see the sign which is growing over time, and this is the exponentially growing sinusoid. Alright, so Pratik, you've seen the case where alpha is greater than 0, it is 0.8 in this case. What if I keep alpha negative, what will I see?
Well, if you keep alpha negative, the exponential will decay, and as a result the amplitude of sine will also decay, and you will just get the same graph just flipped about the y-axis.
That's perfect.
The mirror image of this graph.
That's perfect. So here you can see what is called as the exponentially decaying sinusoid. Of course, it's important to mention exponentially because it can decay in other ways, and yeah, it's quite simple enough. In this case, we've taken alpha as negative 0.4, and Pratik, can you think of some application where we can use this signal to represent something?
Well, there are many physical phenomena which will give rise to sinusoidal waves. So if the sinusoidal wave decays over time, say because sound attenuates, so if the sound is from far away from the source, the amplitude of the sound is lesser.
That's perfectly right.
Yeah,
so speaking of sound, we can talk about music. That's my favorite application of signals and systems. And as you can see in the graph reduces over time. Just like you pluck a string, if you hear the string, it will be loud in the beginning, and as time progresses, the amplitude of, or rather the loudness of the string reduces over time. Of course, a string is not just a simple sinusoid, but that's a story we'll see later on in the course. Okay, so now that we've studied exponentially decaying and growing sinusoids, I'd like to talk about another notation for complex exponentials, and we get that from Eulers' formula, and those of you who studied complex analysis would have seen this before. It is e raised to the power of j omega t. And according to Euler's formula, that is cos of omega t plus j times sine of omega t. Those of you who are mathematicians and not electrical engineers would probably wonder what j is. In electrical engineering, we use j, which is the same as I, that is the square root of -1. We don't use I very often because I is also used for current, and we don't want to confuse notation. So this is the complex exponential, this is Euler's formula, and very simple formula. And of course, we can add phase as well. So you can see in the second case, we put e raised to the power of j times omega t plus phi. And that looks like cos of omega t plus phi plus j times sine omega t plus phi. Alright, so this is the complex exponential. We can of course plot each part, the real part and the imaginary part. So the imaginary part is on top and the real part is at the bottom. Right, so we have the complex exponential. We can take it further, and I'd like you the students of this course to tell me what this plot would look like. So I have e raised to the power of sigma plus j times omega t plus phi, and I want you to tell me what this plot would look like, what would the real part look like, what would the imaginary plot look like, plot some graphs, show it in the forums, and I have some more questions for you. So we've discussed one application, so we discussed the application of the decaying exponential. I'd like you to tell me applications of every other signal we've discussed. So take a physical phenomenon and tell me how we can apply one of these signals to model those physical phenomena. So that's another question for you. The third question I'd like you to solve is, you've seen the complex exponential and Euler's formula. This can be plotted really nicely using a 3D graph, and you get a really nice figure. So I'd like you to do that. So those of you who can plot 3D figures, I'd like you to plot a 3D figure for e raised to the power of j omega t and show us in the forums what it looks like. And from this 3D figure, you can also see which part is the cosine part, which is the sine part, that's the real and imaginary part. And if you can do that as well in the forums, it'll be interesting. So 3 questions for you. The first question would be, what would this signal look like? And the second question is, give me examples of physical phenomena where you'd use the other signals to model them. So the last question would be to plot e raised to the power of j omega t on a 3D graph. Right? So I'll see you in another video. Thank you.